Hi guys, and welcome back to my channel. In this video we'll discuss zero-point energy and a really important consequence of zero-point energy, which is called the kinetic isotope effect. So just as a refresher, we talked about zero-point energy when talking about the particle in a box, and just the idea is that a particle can never have 0 joules of energy. There can never be zero energy, because that would sort of violate the uncertainty principle. Because if the particle had 0 joules of energy, then we would know that it is perfectly still. We would know that it has 0 momentum, and that violates the uncertainty principle because there's always some uncertainty of the position and momentum of a particle. So just as a review, when we looked at the particle in a box and we derived the energy levels, we saw that the lowest energy level, which is called our 0-point energy, was given by E sub 1 equals h squared over 8ml squared. And we derived the formula that E sub n equals n squared h squared over 8ml squared. But because the lowest n value was 1, to get the 0-point energy, we just plugged in 1. So we got E1 equals h squared over 8ml squared. This is an example of 0-point energy when we're looking at electronic energy levels. We're seeing that the energies that electrons have, right, in the particle in a box system. But this idea of 0-point energy also extends to vibrational energy levels. So if we think of a bond, right, we can think of a bond as sort of like a spring. It's squishing and compressing and expanding back and forth and back and forth. There's never a bond that's perfectly still, that's never compressing or expanding, because there is a 0-point energy. There's this sort of minimum energy that the bond has. And so this is sort of what we're going to be discussing in the later slides, and how this leads to a really important effect called the kinetic isotope effect. We can model bonds as a harmonic oscillator, because bonds are basically like springs in that they vibrate very similar to springs. So we can use our physics laws that we know describes springs to describe a bond. So if we treat a bond like just two masses on the side of a spring, and say we compress this bond, so this bond is squished together, there's going to be a repulsive force, and this repulsive force is described by Hooke's law. And the magnitude of this force is given by K, which is the spring constant, describes how stiff the bond is, times the displacement from equilibrium, times your x. And as you can see in Hooke's law, we have a negative sign, right? That's because it's opposing the direction of your displacement. So say I compress this bond, right? Then my force is going to want to push outwards. If I extend this bond, my force is going to want to push inwards. So it's opposite to the displacement, which is why we have the negative sign. So we know that force equals negative kx. That's Hooke's law. We also have from Newton's second law that F equals ma. But in this case, we have F equals mu times A, where mu is our reduced mass of the system. Because we have two masses at the end of the spring, we don't just have one mass. So we have to use something called reduced mass. How do we calculate the reduced mass? The reduced mass is calculated in this way. 1 over mu, 1 over our reduced mass, is equal to 1 over m1 plus 1 over m2, where our m1 and m2 are just the masses at the end of the spring. So then we know that F equals mu times A. The acceleration is just the second derivative of position. So we can substitute that, where we have F now equals mu times d squared x over dt squared. Now we have two expressions for the force, right? We have the Newton's second law expression and we have the Hooke's law expression. So we can set these two equal, and now we have a differential equation we can work with. So in the last bullet point, we've set these two equal. And when we solve this differential equation, we get something of the form x of t. So we get the position function equals some a cosine 2 pi times the frequency times t. So the exact equation is not very relevant, but the frequency is really important. Our frequency is given by 1 over 2 pi times square root k over mu. And this is a really important expression, and we're going to use it later on. Okay, so now let's talk about vibrational energy levels. When we solve the Schrodinger wave equation with the potential function of a spring, so remember that we had Hooke's law equals negative kx, force equals negative kx. If we integrate this to find the potential, we get that the potential function of a spring equals half kx squared when we look at a harmonic oscillator approximation. And this you learn in physics when you take a physics class. If we solve the Schrodinger equation with this potential function, we get E sub n, so again we have our n being our quantum number, equals n plus half times h times our frequency. Where our frequency, remember as we solved in last slide, is equal to 1 over 2 pi root k over mu. So we can see that our energy levels are proportional to this sort of frequency. And another thing to note is that n can equal 0, 1, 2, or any integer above greater than or equal to 0. And this is really important, right? When we talked about particle in a box, we saw that n could not equal 0 for particle in a box, right? But for vibrational energy levels, n can equal 0. So this is an important distinction and something to note. So also for vibrational energy levels, we have something interesting where only energy transitions are allowed when delta n equals plus or minus 1. So what does this mean? If I look for the delta energy, right, when I have a plus or minus 1 transition, I take E sub n plus 1 minus E sub n, and if I plug this in, I get that all the energy transitions are h times my frequency. So basically, any change in energy between two of these vibrational energy levels have the same exact difference. So if I drew an energy diagram and I had n equals 0, n equals 1, n equals 2, blah, 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 all of these things are the exact same energy apart. So if this is delta E, this is also delta E, and n equals 3 would also be delta E. They're all the exact same energy difference, and this is equal to h times the frequency. This is really different from electronic energy levels we thought about before. When we looked at, say, the electron energy levels in a hydrogen atom, we saw that as n increased, as we got farther out in the atom, right, the energy levels got closer and closer together. Whereas when we're looking at these vibrational energy levels, the energy levels are the exact same space apart, no matter what your value of n is. Another really important thing to note is to look at the 0-point energy, which is what we'll be focusing on later on, and this will be really important for the kinetic isotope effect. So remember, our 0-point energy is our lowest energy. And in this case, n equals 0 is allowed, right? So we have our E sub 0 equals, if we plug n equals 0 into the energy level equation, we get that E sub 0 equals half times h times our frequency, which equals half times h times our frequency, which was 1 over 2 pi square root k over mu. So here I just wanted to show how you can see 0-point energy visually on a graph. In this graph, we can see that there's bond length on the x-axis, and we see that potential energy is on the y-axis. So this graph basically shows, say I have a bond where I have two atoms, and I have I'm modeling it as a spring system that's connecting these two atoms. Now, what is the potential energy given different bond lengths? So the lowest potential energy is going to be what the actual bond length is, right? That's going to be the most stable length of the bond. And that we call the 0-point energy. The 0-point energy is basically what is the lowest energy, vibrational energy, that this bond can be at. So this minimum that we see that's starred is the 0-point energy. So again, the lowest energy of the bond is the 0-point energy. And now I want to look at the two different curves that we see. We see a harmonic approximation, which is the red curve, and you notice that this sort of looks like a quadratic function, right? This looks like a parabola. And we also see this Morse potential. So there are two different curves sort of modeling the potential of a bond. So which one is more accurate, right? Let's first look at the harmonic approximation. So this is basically treating the bond exactly like a spring. And if you remember, we talked about Hooke's law. And if you integrate this Hooke's law equation to get potential energy, you'll end up with the potential equals half times k times x squared. The exact equation is not important, but what you should see is that this is a quadratic expression, which leads to our parabola shapes for our harmonic approximation. Now you can see that below the 0-point energy, the harmonic approximation and the Morse potential line up basically the exact same. They're very, very similar. But when we go to bond lengths above the 0-point energy, so bond lengths greater than the minimum energy bond length, so to the right of this star, we see that the Morse potential and the harmonic approximation diverge. Right? We see the harmonic approximation as our bond length goes up. So as our bond length goes up in the harmonic approximation, we see that the potential energy also goes up, and it goes up infinitely, right? That's because this is a quadratic expression, and if our potential equals half times kx squared or some parabola type thing like that, that means that as bond length or x goes to infinity, our potential energy is also going to go to infinity. But instead, our Morse potential does something a little bit different, right? As our bond length goes up with Morse potential, as our bond length goes up, what happens to our potential energy? Our potential energy approaches some certain value. So in this case, we see on this graph, our potential energy is approaching 1.0. So it's just approaching some value. This is a super important distinction, and now we're going to talk about which one models an actual bond better. So the Morse potential models the actual bond better. And why does it model an actual bond? Say for a spring system, say we treated a bond just like a spring. If I pulled the two atoms really, really far apart, and there was still a spring connecting them, there's going to be a massive sort of force pulling back. And that's why our harmonic approximation, which is our spring system approximation, gives a really, really high potential energy. If I pull this far apart, there's going to be a really high force that's really unstable, right? But with our Morse potential, as we increase our bond length, as we pull these atoms really, really far apart, the potential energy doesn't really go to infinity. It sort of asymptotes out. And why is this? Because when I pull the atoms really, really far apart, there's not really an interaction anymore, right? The spring is basically gone. Our spring that was holding these atoms together, our bond per se, is kind of broken, right? So as I pull my atoms farther and farther apart, the actual spring here becomes sort of weaker because there's not as much of an attraction between the atoms, right? The electronic effects, the attractions between the protons and the electrons that's holding this sort of bond together is not as strong. So as I pull the atoms apart, I'm eventually just going to break the bond. And that's what happens with the Morse potential. So in our Morse potential, we can see as bond length goes to infinity, that basically means I've broken the bond. There doesn't exist any bond anymore as my bond length goes to infinity. My potential energy approaches some finite value, and that finite value is the potential energy of both the atoms separated without a bond connecting them. And that's why the Morse potential describes our actual bond much better than the harmonic approximation at bond lengths that are higher than the bond length at which our at which we have our 0-point energy. So another key thing to notice is that our minimum on both graphs, right, if we look at our harmonic approximation, the red curve and the green curve, they both have really similar minimums. And if you remember that when we derived our expression for the vibrational energy levels for our 0-point energy, Schrodinger actually used the half kx squared potential to derive these energy levels when we plug that into the Schrodinger equation. So we actually found the 0-point energy for the harmonic approximation. But this isn't a bad thing, right? Even though the Morse potential describes the bond better overall, the harmonic approximation basically agrees with the Morse potential at the 0-point energy, because you see these minimums of the curves are basically the same. So this should affirm that we can use our expressions for 0-point energy that we previously derived without thinking that we're doing something wrong. Another thing I want to mention is that what is the energy we need to break a bond, right? Our bond is naturally at the 0 point energy, at the lowest energy state we can be. So normally our bond is going to be at this energy level. On this graph, it's denoted as 0. What do we need to break the bond? To break the bond, we need to add enough energy such that we take our bond, which is at the 0 point energy, and go from that energy state to the energy state where the atoms are separated. And if you remember, when we looked at the Morse potential curve, the energy state when the energy at which our atoms are separated is equal to 1.0 on this graph. It's equal to the energy that the Morse potential curve approaches as our bond length goes to infinity, right? So in this curve, we have to go from 0.0, our 0 point energy, all the way to 1.0. We need to add this much energy into our system in order to break the bond. And this is a key thing we'll be using on the next slide to describe the kinetic isotope effect. So now let's talk about the kinetic isotope effect. And this is really, it just comes from the idea of 0 point energies. So say we have a reaction in which we're breaking a CH bond or a CD bond, where D is deuterium. So say we have a CH bond and a CD bond, and it's going through the same exact type of reaction because deuterium and hydrogen have the same sort of reactivities, but one is going to go faster than the other. And the reason that one is going to go faster than the other is because of 0 point energies. So we're trying to break both these bonds, right? And remember that the 0 point energy of a bond is equal to half times h times the frequency, right? That's our 0 point energy. And our frequency is proportional to square root k over mu. Okay, so note that CD bonds, right? Deuterium is heavier than hydrogen. So CD bonds are going to have a greater reduced mass than CH bonds. So that's really important. They're going to have a greater reduced mass than CH bonds, but the K is going to stay pretty much equal because the K has to do with electronic effects. It has to do with how strong is this bond, right? It has to do with what is the attraction between the carbon and the hydrogen. But because hydrogen and deuterium both have the same amount of protons and electrons, the sort of general attraction is going to be the same. It's just going to be the mass of the deuterium that's different. So K is going to be the same, but our mu is going to be greater for a CD bond. So what does this mean? Now if we look at our equation, right, 0 point energy is proportional to square root k over mu, but for 0 point energy of CD, right, our mu is greater, so that means our 0 point energy is lower. So due to the higher mu, the 0 point energy of the CD bond is lower. Okay, so what does this mean? The CD bond takes more energy, therefore, to break than the CH bond. Why? Because remember, we have to overcome the 0 point energy in order to break the bond. So if it takes more energy to break a CD bond, that means the speed at which the CD bond is broken will be slower than the speed at which the CH bond will be broken. Just think of it like activation energy. It takes more energy for me to break the CD bond. So in general, there's going to be more of an energy barrier for me to break the CD bond. So it's just going to go slower because there's a higher energy barrier. So this is what the kinetic isotope effect basically is. Reactions involving breaking bonds with heavier isotopes are slower than reactions involving breaking bonds with lighter isotopes. Why is it slower? Because with the heavier isotope, your 0 point energy is lower, and in order to break the bond, you need to overcome the 0 point energy. So you have more energy to overcome when you have a heavier isotope, and because you have more energy to overcome, the reaction or the breaking of the bond will go slower. So in this slide, I just wanted to give an actual example of where the kinetic isotope effect is used. One of the uses for it was proving the E1 mechanism, and this goes into a little bit of organic chemistry, which I'll just briefly touch on since this isn't an actual organic video, but I just want to give you some background. So what is E1 and what does that stand for? The E stands for elimination, and this is a common reaction type that you'll see in organic chemistry. The 1 stands for first order. The other very common elimination reaction is E2. Again, the E stands for elimination, but the 2 stands for second order, and that should make sense. So first order and second order, that's basically like in the rate laws, we have a first order reaction and a second order reaction. Here I've drawn the same organic compound twice, and I just want to show how an E1 and E2 mechanism would occur with this specific organic compound. So when I draw these diagrams, the vertices have carbons, and the hydrogens are implied, giving all of the carbons 4 bonds. So with elimination reactions, right, we always have a base involved. So I'm going to have the left one be an E1 and the right one be an E2. For an E1 mechanism, what happens is the bromine, we call this the leaving group. The leaving group leaves, and what happens is this leaves a carbocation. Because now the bromine has taken both the electrons that were with it in the bond, and it leaves the carbon with an incomplete octet, right? There's only 6 electrons now for the central carbon. Now what happens is the base comes in, there's the base, and deprotonates one of these hydrogen atoms, right? It takes this hydrogen off, because that's what a base does. If we think of our Bronsted-Lowry definition, it accepts protons. And then this forms a double bond. So what we end up with is a product that looks like that. Now let's look at the E2 mechanism. And in the E2 mechanism, we have all of this happening in the same step. The bromine is going to leave and the hydrogen is abstracted, all in the same step. So we have our base that deprotonates this hydrogen, and then we eliminate, and then the bromine leaves. And as we can see, this forms the exact same product, right? So how do we differ between both of these? How do we differ between these two mechanisms? How do we know that E1 is different than E2, and that both of these mechanisms are at play? How do we know that it's not just E1 or just E2, right? As we can see with E1, there's sort of 2 steps. We first have the bromine leaving, and then we have the deprotonation. Now I want to think about rate determining steps, right? This is what we sort of want to think about when we're looking at this kinetic isotope effect. When we look at the rate determining step of the E1 reaction, the rate determining step is the bromine leaving. So with the E1, we have rate determining step being the bromine leaving. Why is this the rate determining step? Because when the bromine leaves, we leave the carbon with an incomplete octet. It only has 6 electrons. This is super unstable, right? No atom except for, some weird exceptions like boron and aluminum want any less than 8 electrons. Every atom wants an octet. So when the bromine is leaving and taking the electrons with it, this is super unfavorable. We have a huge jump in energy. That's why this is the rate determining step. There's a huge activation energy barrier. So bromine leaving for the E1 reaction is our rate determining step. Whereas in E2, all of this is happening in the same step. So the rate determining step is the only step, which is hydrogen abstracted, right, and bromine leaving. But the hydrogen abstracted is part of the rate determining step, whereas in our E1, only the bromine leaving is part of our rate determining step. How can we use this as something to tell us the difference between E1 and E2? Say we now instead had the same compound, but that looks like this, where we replaced all the hydrogens with deuteriums, right? When we look at the E1 reaction, should this go any slower? No, because the rate determining step only has bromine leaving. The bromine can leave the exact same way as in the reaction we just talked about where we had hydrogens instead. Whereas with E2, does the rate determining step, does this slow down the reaction? Yes. Why? Because now we have deuteriums instead of hydrogens, and the abstraction of the proton, the abstraction of the hydrogen or of the deuterium is part of the rate determining step. And if you remember, when we break a bond, when we break a CD bond, that takes more energy because of the lower 0 point energy of the CD bond compared to the CH bond. So the breaking of the CD bond takes more energy, which means that it goes slower. And because with E2, we're breaking the CD bond and we're breaking the CH bonds in the rate determining step, when we replace the hydrogens with deuteriums, the reaction for E2 will go slower, whereas the reaction with E1 will not go slower. It'll stay the same rate. This is a key example of how kinetic isotope effect was actually used to show the difference between the E1 and E2 mechanisms. So thank you guys so much for watching. This was all I wanted to cover today. If you enjoyed these videos, I hope you'll stick around for some more content. Thank you again for watching, and I'll see you in the next one.